it's really useful to remember where sines and cosines ultimately came from, which is the unit circle, by which I mean a circle whose radius is 1. So if we go ahead and we draw a line that makes an angle of theta with respect to the x-axis, and so that the other end terminates on the unit circle, then my sines and cosines are nothing more than the x and y component of this line. Another way to think about this is, remember we introduced Euler's formula, which is e to the I theta is cos theta plus I sine theta. And we had talked about the Argand diagram, where we plot the imaginary component of a number on the y-axis and the real component on the x-axis. And so what we have in this case is basically a repeat of the unit circle, where e to the I theta, it has a magnitude of 1, and the angle that it makes with respect to the real axis is theta. So this just kind of leads us to think about sines and cosines as lines rotating around a circle. So that kind of brings us to the idea of phasor. Now this is spelled differently than the phasor from Star Trek. This is P-H-A-S-O-R-S. And essentially what we're going to do is use a vector to represent the amplitude and phase of the wave. And so what I mean is, rather than drawing the typical sinusoidal wave to represent this, we're going to draw a vector whose length is equal to the amplitude of the wave and whose angle with respect to the x-axis is equal to its phase angle. So right here, for this point, we would draw a phasor of length a that makes an angle of theta equals 0 with respect to that axis. This point right here then, which makes a phase angle of pi over 4, is represented by a vector of length a and an angle of theta equals pi over 4. The peak of my curve then corresponds to a phase angle of pi over 2, and so we draw that as a vector of length a and angle theta equals pi over 2. Now one thing to notice is that the wave then corresponds to the y component of the vector. So over here we have a y component of 0. Here our y component corresponds to the sine of 45, and then here our y component is just equal to the amplitude. What this does mean is that if we are representing a wave with a cosine function, then we have to shift that cosine into a sine function in terms of the phase of the phasor. Okay, so our field amplitude is always going to correspond to the y component, which means sines are fine, and you can just take the phase angle of a sine. So if you have sine kx minus omega t, that then is the angle of your phasor. But if you have cosine kx minus omega t, the angle of your phasor needs to have an additional pi over 2 term in it, which kind of brings us to talking about the phasor of a traveling wave. And so here is the length of our vector, and this then is the phase angle, or the angle that it makes with respect to the y-axis. Now one thing to notice is that as time progresses, this is going to rotate around the circle. Same thing as x advances. We have essentially a spinning vector. And so one way to sometimes visualize this is as the hands on a clock that are either rotating counterclockwise or clockwise, depending on what exactly you are looking at. And so these phasors are essentially spinning as time progresses, or spinning as you move through space.